how to get GCD using Java code.
Now, we will explain the Java code for finding the GCD using the Euclidean algorithm. This is the simplest and most common implementation. So I'm gonna explain it line by line. First is the class declaration. So public class Euclid GCD. So this line, I declare that this is the class name of my GCD. And all our code is written inside this class. So second line is public static int is d int a int b is very common. So this is our method named GCD. It takes two numbers a and b and returns their greatest common divisor or GCD. Third is this while loop. So here we repeat the process as long as b is not 0. The Euclidean algorithm stops when the second number becomes 0. Fourth is the fourth line is this line computes the remainder when a divided by b. So this is the key step of the Euclidean algorithm. Fifth is then we update our values. So the old b becomes new a, the remainder becomes the new b. This matches the steps we do manually when solving GCD. Then we return a. When b becomes 0, a now contains the GCD, so we return it. As in the main method, this is the main method where our program starts running. Here we choose numbers, for example, 252 and 205. Here we call our GCD function and store the answer inside the variable result. So this is the output. This line prints the final result of our computation. When we run this program, the output will show that GCD of 252 and 105 is 21. This confirms that our Java code follows the Euclidean algorithm correctly.
I challenge anyone. No one can defeat how greater I am.
Hoy, ako ang kalaban mo. I-divide mo ako kung kaya mo.
Guys, please behave. We're mad, not drama.
A few inches later.
In this study, we simulated the Euclidean algorithm using a real-world coding setup. Why? Because we wanted to measure how efficient the algorithm is when using three basic operators like subtraction, division, and modulo. Since the Euclidean algorithm is a key method for finding the greatest common divisor or GCD, analyzing its speed helps us understand which operator makes it perform better. Now, let's talk about figure 1. When the algorithm was tested without any input value, something interesting happened. Subtraction turned out to be the fastest. Yup, the simplest operator took the lead, fast and straightforward. Subtraction didn't hesitate. Next is figure 2, with input values. Moving to figure 2, we tested the algorithm with actual values, and here, the behavior changes. As the number gets bigger, the algorithm naturally becomes slower. But there's a twist. The operator used affects how slow or fast the algorithm becomes. Among all three operators, modulo was the fastest, especially when performance was measured in milliseconds. It handled large input values more efficiently than subtraction and division. Across all simulations, the Euclidean algorithm consistently produced the correct GCD, no matter which operator was used, so accuracy wasn't the issue. The difference was the speed.
So I will discuss the strengths and limitations of the Euclidean algorithm. One of its main strengths is its fast performance, with a time complexity of O of log mean AB, making it very efficient in finding the GCD for both small and large numbers. It is reliable, scalable, and uses only basic operations like subtraction, division, and modulo. So in addition, all three methods, prime factorization, log division, and Euclide's division algorithm are used to find the greatest common divisor and are mathematically reliable, but they differ in speed and practicality. Prime factorization becomes slow for large numbers. Long division is moderately efficient, while a Euclide's algorithm is the fastest and simplest. Therefore, Euclide's division algorithm is the most efficient overall, especially for large numbers and real-world applications. To summarize the Euclidean algorithm, first is divide the largest number by the smallest number. Second is get the remainder. Third is repeat the process until the remainder is 0.
The last remainder is the GCD.
It's a simple, efficient, and reduced technology.
We hope this discussion help you understand the Euclidean algorithm in a fun way.
Math doesn't have to be boring, but sometimes you try it.
As long as you understand the logic, kaya mo to.
Thank you for watching!